Hello friends, warm welcome to the channel World of Zoology. In the today's lecture, which is the series on the topic instrumentation, we'll consider the next point, which is Sorensen's pH scale and pH meter with respect to our 3 points, that is introduction, then application and principle. We'll consider the first, that is Sorensen's pH scale, and in that we'll consider introduction of both. More than three-fourths of the Earth's surface is covered with water. Similarly, the amount of water in human body ranges approximately to about 70%, and the range is given as 50 to 75%. Water is critical for existence of the and survival of the living organism. That is, it is essential for existence and survival or sustenance of the living organism. It is therefore inevitable that all life forms have interact with hydrogen ions. The central agents of life, that are various enzymes which are involved in the catalysis reactions necessary with exquisite selectivity. Most enzymes are very sensitive and can function effectively in very narrow range of hydrogen ion concentration. That is, these enzymes are very sensitive and they cannot work if we change the pH of that particular system or the enzyme assay, because the particular pH which is known as optimum pH for that enzyme activity and other pH may not be the same, and that may cause changes in the protein structure of the enzyme, and it affect the catalytic activity by causing denaturation of the enzyme, and therefore role of pH in that particular enzyme is very specific, which catalyze the particular enzymatic reaction. Most enzymes are therefore sensitive and can function effectively in very narrow range of hydrogen ion concentration. Therefore, it is important to understand the relationship between the water and the life solvents and hydrogen ion concentration of the life systems. Given the amount of hydrogen ions in the biological systems and need to conveniently express it, Sorensen introduced a scale for expressing hydrogen ion concentration in terms of numbers called pH units. Here, we must consider that the Sorensen scale assigns a pH of 1 to 14, with 1 being most acidic and the 14 number being most basic, and 7 which is neutral value, neither acidic nor basic. The pH scale works in the power of 10. That means each jump in the number is a multiple of 10 in concentration. That is, for example, a pH of 1 is 10 times more acidic considered with the pH of 2, or pH value of 3 is 10 times less um, with respect to the acidic nature compared with the 2, and likewise. Here, Sorensen's scale is given. The hydrogen ion concentration in biological system that ranges from about 10 raised to 2, that is 10 raised to minus 2 means pH is equal to 2 moles per liter, as in the gastric juice in case of the human being in the stomach, or the value may be 10 raised to minus 7.45 moles per liter as in case of the human blood, and Therefore, it is approximately given as pH is equal to 7.45 to about 10 raised to minus 9 mole per liter in case of the lime water. Overall, as the most important concentration in acid-base reactions, as also in various biological processes, is that of the proton, that is hydrogen ion, and in aqueous medium, its concentration may vary from something like 10 raised to minus 15 to 10 mole. It is easy to understand that the large variation in concentration in terms of expression are inconvenient to use. Here the Sorensen's pH scale is given, where the acidic range and alkaline range is shown with respect to the little difference. The difference may even small, but the decline in the pH value from 1870s to 21st century would mean a 170% increase in the acidity, and much smaller changes already pose problem for many sea animals or the creatures. Here the scale shows the most acidic, that is HCl, hydrochloric acid, which is very acidic, that is having value of pH 1. Then comes the Coca-Cola with pH value of 3. Then wine, which is again acidic with pH value of 4. Then slightly acidic solvents like mineral water having pH value near about 6. Then comes the pH value for the blood, that is 7.45, the blood pH. Here the average pH value of seawater is shown in uh, 21st century, and the pH value which is in 1870 is also shown, that is 8.18. Then the alkaline range, it starts slightly alkaline, that is soap. Then it ranges between 8 to 9. And then again more alkaline is the laundry or the detergent powder, having the alkalinity of the value 10, and very alkaline solution which is shown as the NaOH solution with pH value, that is 14 in this diagram. With a view to simplify the method of expressing the hydrogen ion concentration, the Danish biochemist Sorenson in 1909 suggested a scale in terms of easy to use simple numbers. He expressed concentration as a pH originally, which is written as P to the base H in terms of its negative logarithm, thereby eliminating the need to use exponential terms. He defined hydrogen ion concentration, which is given below. pH is equal to negative logarithm of the H plus ions, that is hydrogen ions. It is common knowledge that water is weak electrolyte, means it does not freely dissociate. However, it would auto-ionize to give cation and anion. It could be said that the one molecule of water reacts with other water molecules so as to produce H2O plus H2O, that gives rise to H3O plus OH, H3O plus OH minus. The species of H3O plus and hydrated proton is called as the acid, while the species OH minus is called as the base. The dissociation can be still simplified and shown as below, that is H2O that gives rise to H plus OH minus ions. Thus, one water molecule can produce one H plus and one OH minus ion. Applying the law of mass action, The equilibrium constant for this reaction can be shown as K is equal to H plus into OH minus divided by H2O. Since 100 grams of water contain 5.5 moles of water, concentration of water in this reaction may be practically considered as constant, and so a new constant which is given as KH2O is equal to Kw may be brought about to correlate the product of two ionic species in the equation for dissociation of water. Kw is equal to H plus and OH minus. Here Kw means ionic product of water, and therefore Kw may be called as ion product of the water and has been found to have a value of approximately 1 into 10 raised to minus 14. As one molecule of water gives one proton and one hydroxyl ion, that is H plus, and one OH minus, the concentration of hydrogen ion and that is H plus ion and OH minus ion, that is hydroxyl ions, in neutral water must be equal. Therefore, H plus ions equal to the OH minus ions. So, Kw, that is ionic product, is equal to H plus square. That means as H plus ions equal to the number of OH minus ions, means they are same in the number, and therefore Kw, that is the value of the ionic product, is equal to H plus square, and therefore H plus is equal to square root of Kw, that is ionic product. Type equation here which is given in case of the neutral water, the concentration of hydrogen ion would be 10 raised to minus 7 at 25 degrees Celsius in case of neutral water. It must be remembered that like most chemical reaction, auto-ionization reaction of water is also temperature dependent. So the concentration of hydrogen ions in neutral water would change with the temperature change. The concentration of hydrogen ions would also change every time water enters into the chemical reaction, as also when other reactant react in aqueous medium. Thus, when the compounds like methyl acetate hydrolyzes, that is, it react with water to produce acetic acid, thereby increasing the hydrogen ion concentration of the reactant medium, and that is nothing but the water. Also, when hydrochloric acid dissociates in water to give hydrochloric acid means HCl, that dissociate to give H plus and Cl minus ions, it increases the hydrogen ion concentration. Similarly, when the sodium hydroxide, that is NaOH, dissolves in water, it produces OH minus ions and Na plus ions, thus reducing the hydrogen ion concentration. Interestingly, certain chemicals or a combination of chemicals have a capacity to resist change in the hydrogen ion concentration. When the systems in which reactions are occurring are subjected to addition or deletion of the hydrogen ions, such action of limiting the hydrogen ion concentration within a certain range is called buffering action, and the reagents here are known as buffering agents or simply the buffers. That means here buffers are the substances that resist change in the pH. The range within which they exercise such a control is called as buffering ability of that particular buffering agent. The buffering capacity is the ability of the buffering agent to resist a change of one pH unit. For instance, solution of the strong acid such as HCl, or that is hydrochloric acid, or strong base such as NaOH resist any change in the hydrogen ion concentration almost till their neutralization points are reached. A 100 ml solution of 0.1 molar HCl will register a change in the hydrogen ion concentration of 1 pH unit till more than 99.999 ml of 0.1 molar solution of sodium hydroxide is added to that, or added into HCl. As such, this should prove very effective in controlling the pH of the solutions and hence be excellent buffering agents or the buffers here. However, such strong acids or strong base buffers would be operative in extreme regions of the hydrogen ion, that is pH scale, that is the systems that are highly acidic or the systems that are highly basic. Most biological reactions occur in a much varied range of pH. Later, the which is corrected to equation pH is equal to negative log A to the base AH, where AH is the activity of the hydrogen ion rather than its concentration. The activity of the hydrogen ion is related to concentration by an equation. AH, that is activity of hydrogen ion, is equal to A approximate proton activity. Here H plus means proton, where approximate is the activity coefficient that depends upon the total ionic environment of the particular solution to avoid the confusion between the use of theoretical pH scale in terms of activity of the hydrogen ions and that on concentration. A practical scale is defined in terms of a specific buffer mixtures that in a way are believed to be approximate the proton activity. Here A and the sign which is given is approximate and H plus means proton. A H plus means approximate proton activity. Here activity is the number of moles per liter, or the approximate A means the concentration in moles per liter. For example, an equimolar solution of acetic acid and sodium acetate is expected to give pH as 4.75, which is also the concentration of hydrogen ions in the solution. The pH meter is then calibrated to read 4.75 when the pH scale is immersed in such a solution. Then pH measurement of unknown solution in a range close to this would relate to the concentration of hydrogen ions. This may be expressed as pH is equal to log 2 divided by H plus ion. We know that Kw, that is ionic product of water, is equal to H plus into OH minus. Or here we can rearrange the equation as H plus is equal to Kw divided by OH minus. Taking natural logarithm of both sides, we can write the log H plus is equal to log Kw minus log OH minus. Rearranging the terms, we can get log minus log Kw is equal to minus log H plus minus log OH minus. Therefore, we can get pKw is equal to pH plus pOH, means power of ionic product of water is equal to power of H plus power of OH minus. Since concentration of neutral water is about 1 into 10 raised to 14 moles per liter at a temperature of 25 degrees Celsius, and remembering that H plus, that is proton, is given as square root of Kw, since H plus is equal to OH minus, pKw is equal to 14, and so pH is equal to pOH is equal to 7, which is for neutral water. A pH of less than 7 values therefore indicate that the sample or the solution which is given or being studied is acidic, while the pH value greater than 7 indicate that the particular sample is basic in character. It is then possible to classify substance on the basis of this scale as the acidic, basic, or even the neutral value of the particular substance on the basis of their pH values. Now we consider the next part of our lecture, that is nothing but the pH meter. pH meter is a scientific instrument that measures the hydrogen ion activity in water-based solution, that is aqueous solution, indicating its acidity or alkalinity, which is expressed as pH. Therefore, pH meter is an instrument used for measuring the concentration of hydrogen ions in a given sample or given solution. It uses Nernst equation that relates the electrode potential of an electrode with concentration, or more correctly we can say the activity of the given ion in a solution. For example, an electrode or cell which is reversible to hydrogen ion will relate its potential to the concentration or the activity of the hydrogen ion in a given solution. The instrument consists of combination of an electrode system of an electrode that is reversible to hydrogen ions and standard reference cell connected to a special type of potentiometer. Now we'll consider the next point, that is nothing but the principle of the working of the pH meter. The potential of an electrode reversible with respect to the hydrogen ion is governed by the activity of the hydrogen ions in the particular given solution. The activity of hydrogen ion may be considered as its effective rather than the actual concentration. This is because a carrier of positive charge, the hydrogen ion, exerts electrical force on its surrounding. Carrier of positive charge means here H plus ions. The same may be said for the negatively charged, that is hydroxyl ion OH minus. While the solution itself might be electrically neutral, on macroscopic, that is large scale, the effect of ion can be drastic at the microscopic, MICRO means smaller scale. Solutions with relatively high concentration of hydrogen ions may yield lower determination of its concentration. Therefore, the aqueous solution, that is solution prepared in water, begins to behave as if some of the ions are no longer present. This apparent loss of ions is caused by interaction of ions which are present in solution, ultimately resulting in the significant deviation from the ideal behavior. In order to take this interaction into the account, the ion activity or the effective ion concentration needs to be considered rather than only ion concentration. Means effective ion concentration or the ionic activity is considered rather than the ion concentration. As such, pH gives a measure of hydrogen ion activity rather than its actual concentration. The activity concept need not bother or it need not bother us too much in understanding or the use of the Sorensen scale, as relation between the activity and concentration is linear one, which is given A H plus is equal to gamma H plus, where gamma is the activity coefficient. As such, the pH reading may be taken as the good indication of the concentration of hydrogen ions. The electrode used in the measurement of the pH is often combined gas electrode. Here combined glass electrode, which incorporates the reference electrode along with the auxiliary electrode. The body of the electrode is made up of non-conductive glass or plastic. The bottom of the electrode balloon out into a round thin glass bulb. That is membranous structure. The pH electrode is best thought of as a tube within the tube itself. The innermost tube contains an unchanging 1 into 10 raised to 7 moles per liter HCl solution. That means the innermost tube contains HCl solution with 1 into 10 raised to 7 moles per liter value. Also in the inner tube is the cathode terminus of the reference electrode. The anodic terminus wraps itself around the outside of the inner tube and ends with the same sort of the reference probe as was on the inner side of the inner tube. It is filled with the reference solution, which is of the zero point 0.1 molar ACl and has the contact with the solution on the outer side of the pH probe by the way of the porous plug, and that porous plug actually serves as the salt breach. Here the combined glass electrode is shown with the inner bulb having 0.1 molar HCl solution and the outer part having the outer bulb having KCl solution with the two anode and cathode terminus to pH meter and AgCl reference electrode which is shown, and internal AgCl reference electrode which is shown here with pH sensitive glass membrane is also there. Some of the important characteristics about the glass membrane electrode are as follows. We'll consider one by one. The potential of this electrode is essentially unaffected by the presence of oxidizing or reducing agents. Second one, it is operative over a wide range of pH values. It is fast responding to changes in the hydrogen ion concentration. It functions well in physiological system, that is in the cellular system. It is very convenient to use. These are some of the important characteristics of the glass membrane electrode. We'll consider now the next point, that is nothing but application of pH meter. How we can use or which are the applications. pH meters are used to estimate the hydrogen ion concentration of a given sample. This helps us in understanding the nature of the sample, whether the given sample is acidic, basic, or it is neutral. Knowing the exact pH of the sample helps us in manipulating the chemical reaction. For example, synthesis of the certain molecule that requires a particular pH to be maintained. This is often so as to form the compound or the synthesis of the coordinate compound, which is possible. Performing acid-base titrations, which are otherwise difficult to perform using coloring acid-base indicators by classical techniques. Using pH meter to perform such acid-base titrations also minimizes the errors of adding excess titrants, since the endpoint is determined graphically and not on the basis of the color change. Second application, that is pH measurement, find its use in pharmaceutical industries where pharma preparations have to be carefully executed at a specific pH, or even synthesis of a drug has to be carried out at a specific pH. In medical science, pH measurement help in clinical diagnosis for various situations such as burning throat, tooth decay, for many other alignments. In dairy industry, maintenance of accurate pH is essential to obtain dairy products such as cheese of the high quality. Next application is the pH measurements, which are important to for wine industry or winery, what we term it as, for making, in order to avoid spoilage of the taste of the wine by contamination due to excess acid being generated during fermentation process. Now the next application is the knowledge of the accurate pH that helps in the maintenance of a swimming pool required for our well-being, because excess pH causes damage to our skin. A proper maintenance of soil pH that helps the cultivator in deciding the type of cultivation to be taken for the good yield, or the which is useful for maintaining the soil pH. Water for consumption and in aquaculture media needs careful monitoring of the pH. We need to maintain the pH for various activities, even in the maintaining pH of drinking water is essential for municipal corporation. That's all. We have finished the Sorensen scale and pH meter here in this lecture. Thank you for watching this video. If you do like the video, share the video for the benefit of the maximum students, and subscribe the channel World of Zoology for the further notification of the next video. Thank you once